Alright, this section deals with polynomial functions and their graphs. And out of that section, we're going to be identifying polynomial functions, recognizing characteristics of graphs of polynomial functions, determining the end behavior of a polynomial function, also use factoring to find the zeros of polynomial functions, and also identify zeros and their multiplicities. We'll start off with the definition of a polynomial function. And it is the function defined by this. F of x is equal to a sub n, x to the n plus a sub n minus 1, x to the n minus 1 plus, and so on, all the way to a sub 2, x sub 2, x squared, plus a1x plus a sub 0. That's a polynomial function of degree n. And of course, there are two things we need to know. A sub n, that's this term right here, or the coefficient of the variable to the highest power or to the highest exponent, that's called the leading coefficient. Okay. And if we remember the word degree, that's always the highest exponent of any polynomial function. So the coefficient of the variable that has the highest exponent would be the leading coefficient. Polynomial functions of degree 2 or higher have graphs that are smooth, rounded curves with no sharp corners, and they're continuous with no breaks and can be drawn without lifting the pencil. So in this case here, let's say we had a graph that looks like this. So to illustrate what a polynomial function would look like, this will be a polynomial function because it does have smooth curves in it, and it can be drawn without lifting the pencil. So here, this will be an example of a polynomial function. What would not be a polynomial function is this. If it's got sharp corners in it, then it would not be a polynomial function like this. That would not be a polynomial function because of those sharp corners there. And also, if there's a break in the graph, then that too is not a polynomial function. Let's say that the polynomial graph goes like this and then comes down this way like this. That would not be a polynomial function because, as you can see, there is a break in the graph. Okay, so keep in mind that a polynomial function has to be a smooth curve that's rounded with no sharp corners and must be continuous, meaning that there's no break in that particular graph. All right, the next term is the end behavior. What the end behavior is defined as the behavior of a graph of a function to the far left or to the far right. Okay, sometimes the behavior could be this. The graph could be going upward on the left side and downward on the right side, or downward on the left side and upward on the right side, or it could be going up on the left and the right and down on the left and the right. That's basically what we mean by end behavior. And we can look at the leading term, which is a sub n, x to the n, to determine the end behavior of a polynomial function. Here we're going to let a sub n be the leading coefficient and n be the degree of the polynomial function. What we're going to be using in this case is the leading coefficient test. That test will determine what type of end behavior we're going to have for any polynomial function. So we're letting a sub n be the leading coefficient and n be the degree of the polynomial function, or the highest exponent in the polynomial function. The sign of the leading coefficient and the degree, or the highest exponent of the polynomial function, will reveal its end behavior. So in this case here, if n was an odd number, or an odd power like 1, 3, 5, 7, 9, etc., then we look at a sub n, which is the coefficient of the variable with the highest exponent. If that a sub n is bigger than 0, then the graph falls to the left and rises to the right. Or if it's negative, if a sub n is negative or less than 0, then the graph will rise to the left and fall to the right. And that only happens when n is an odd exponent. Now, if n is an even exponent, then we go ahead and look at a sub n. If a sub n is bigger than 0, then the graph is going to rise to the left and to the right. And if a sub n is less than 0, then the graph falls to the left and to the right. So here, this is what we call the leading coefficient test that we will use to determine the end behavior of the graph of any polynomial function. Okay, now we're going to look at one example of how to determine what type of graph end behavior we're going to have for that particular graph. Like in this situation here. Here we want to use the leading coefficient test to determine the end behavior of the graph of this function, f of x is equal to x to the fourth minus 4x squared. Okay, so here's the equation or the function. Now we want to determine what the end behavior of that graph. Now we need to identify two things, a sub n and n. The a sub n is the coefficient of the variable with the highest exponent. And here, the highest exponent is 4, so I can go ahead and just write down what n is, because n is the highest exponent of that polynomial function, which is 4. A sub n will have to be 1, because that's like 1x to the fourth. So here, a is going to be 1. And then we're going to look at n to determine whether it's odd or even. N is equal to 4, so that means that's even. Then we go to the a sub n to determine whether it's positive or negative. In this case, it's positive. A sub n is bigger than 0, so the end behavior of this graph would be this. I'll just say this, that f of x, and it's even and it's positive, so that means that the graph of f of x rises to the left and to the right. So the graph of f of x rises to the left and to the right. Okay. All right, now let's look at another example. In this case, we're going to use the leading coefficient test to determine the end behavior of the graph of this particular function. Here we got f of x, and that's equal to 2x to the third multiplied by x minus 1 times x plus 5. Okay, that's this function right here. Now we're going to use the end behavior. Well, use the leading coefficient test to determine the end behavior. Notice that this is already factored out. So we can easily find out what a sub n is, but we're going to have a problem finding out what n is. Now what we're going to have to do here is take the exponents for each x and add them together. For this one, the coefficient of x is 3. For x minus 1, the coefficient is 1. The exponent is 1. And for x plus 5, its exponent is 1. So here I'm just adding these exponents for x. So 3 plus 1 will be 5. So that means that n is going to be 5. That's the highest exponent of this polynomial function. A sub n, that's your 2 right here. Okay. So now we determine whether n is odd or even. In this case, n is equal to 5, so that's odd. And then we go to a sub n, which is 2. That's positive. So here, the graph of f of x, according to the leading coefficient test, okay, it is odd and bigger than 0, so that means that the graph of f of x falls to the left and rises to the right. Okay, so that's basically how you'll use the leading coefficient test to determine the end behavior of the graph of any polynomial function. Okay. Okay, here's an application problem that involves the coefficient test, the leading coefficient test, as I should say. In this case, the polynomial function f of x equals to negative 0.27x to the third plus 9.2x squared minus 102.9x plus 400. That models the ratio of students to computers in the United States public schools X years after 1980. Use the end behavior test to determine whether this function could be an appropriate model for computers in the classroom well into the 21st century, and explain your answer. Okay, so we're just looking at the function itself. I'll write this down on another sheet of paper so you'll see how this is going to be worked. Okay, so here's the function that we're looking at. So we need to identify a sub n and n. Well, n is the highest exponent in this polynomial function, that's 3. A sub n is the coefficient of the variable with the highest exponent, that's negative 0.27. Okay, so now we want to determine its end behavior. Now, n is 3 and it's odd. A sub n is negative 0.27, that's less than 0, it is negative. So that means that the graph of f of x is this. It falls, no, take that back, it rises to the left. And falls to the right. Reason for that, because a sub n is negative, n is odd. Okay, now based on that, let's answer that question. We want to determine whether this function could be an inappropriate model for computers in the classroom well into the 21st century. Based on that end behavior, it would not. Here's why. Because the graph is going to be falling to the right. If it's falling to the right, at some point, the value of f of x will become negative. And it's impossible to have a negative amount of computers well into the 21st century. So this would not be an appropriate model to use in the 21st century. And the reason for that is because we're going to get a negative value for f of x because of the fact that the graph is going to be falling to the right. Okay, so that's how we use that leading coefficient test to determine end behavior. Okay, the next we'll look at is zeros of polynomial functions. Okay, and the definition of zeros of f, or zeros of f of x, is the value of x for which f of x is equal to 0. And these values are the roots or the solutions of the polynomial equation f of x is equal to 0. So what that is that you're taking that polynomial function and you're setting it equal to 0 to find out what the zeros of that function is. And if you were graphing this, by the way, those zeros of that function would represent your x-intercepts of that graph. All right, now take a look at this problem here. We want to find all the zeros of this function. F of x is equal to x cubed plus 2x squared minus 4x minus 8. F of x is equal to x cubed plus 2x squared minus 4x minus 8. Now in this case, we want to find the zeros of this function. So here we're going to set this particular function, f of x is equal to 0. So here I'm going to set x cubed plus 2x squared minus 4x minus 8 equal to 0. And then I'm going to factor this as completely as I possibly can. Now in this case, I have 4 terms, so I need to group the first 2 terms, x cubed plus 2x, and the last 2 terms, minus 4x minus 8. Now let's look at x cubed plus 2x squared. In x cubed and 2x squared, the common factor, of course, is x squared. So I'm going to factor out the x squared. And then to get what's inside the parentheses, I'm going to do x cubed divided by x squared. That's going to give me x plus 2x squared divided by x squared will be 2. So I have x plus x squared times the quantity x plus 2. Now for the minus 4x minus 8, the common factor here is a minus 4. So let's factor out that minus 4. So now minus 4x divided by minus 4 will be x. Then minus 8 divided by minus 4 will be plus 2 equal to 0. Now as you can see, the common factor here is x plus 2. So let's pull that out. And then the other factor will be x squared minus 4. Equal to 0. Alright, now the next thing I'm going to do here is the differences of squares is at x squared minus 4. So let's factor out x squared minus 4. As I know that's the differences of squares, and that can be factored into 2 binomials. One will be x plus 2, the other one is x minus 2. So I get x plus 2 times x plus 2 times x minus 2 equal to 0. Now I'm going to set each binomial factor equal to 0. Now notice I got x plus 2 written twice, but I'm going to write that one time because that factor is going to be what we call a double root. So I said x plus 2 is equal to 0, and then the other factor, x minus 2, equal to 0. And then we're going to solve for x. So for x plus 2 is equal to 0, you're going to have x is equal to negative 2. And then for x minus 2 is equal to 0, if we add 2, you'll get x is equal to 2. Okay. So that negative 2 is going to be a double root, and then the other root will be 2. So here, the solution set would just be negative 2 and 2. Okay. So that's how we find the zeros of any polynomial function. Now this is one of those examples where you have x equal negative 2 being a double root. And it has something that we call multiplicities. We call this negative 2 having a multiplicity of 2 because we got x plus 2 as a factor twice. And when you solve for x, you're going to get x equal negative 2. And that's the next thing we're going to look at in this particular section. Well, later on we'll look at that, but I do have another example of finding the zeros of functions. Like this one, f of x is equal to x to the 4th minus 4x squared. So here we got f of x is equal to x to the 4th minus 4x squared. We set the function equal to 0, so you got x to the 4th minus 4x squared equal to 0. Now we have two terms, so the only thing we can do here is take out a common factor. So for x to the fourth and minus 4x squared, the common factor will be x squared. So we'll factor out the x squared, and then you'll have x to the fourth divided by x squared will be x squared, minus 4x squared divided by x squared will be 4, equal to 0. And then you'll see that x squared minus 4, again, that's the differences of squares, so that can be factored into x squared times x plus 2 times x minus 2, equal to 0. And then we'll set each factor equal to 0. So we'll set the x squared equal to 0, x plus 2 equal to 0, x minus 2 equal to 0. Now for x squared is equal to 0, the only number squared that would give me 0 would be 0, so x would be equal to 0. Now for x plus 2 is equal to 0, if you subtract 2, you'll get x is equal to negative 2. And then for x minus 2 is equal to 0, you'll get x is equal to positive 2. Okay, now notice that x equals 0 is a double root because x squared is like x equals 0 and x is equal to 0. So here, my solution set would just simply be 0, negative 2, and 2. Okay. And just like in that last problem that I just did, we had a double root, so do we. X equals 0 is a double root as well. And that's what brings up this next thing that I wanted to talk about, is the multiplicities of zeros. When you factor the equation for the polynomial function f, if the same factor called x minus r occurs k times, but not k plus 1 times, we call r a zero with multiplicity k. And basically what that is just this. You're just looking at the exponent for that particular factor x minus r. Because that exponent will tell you the multiplicity. Because that in fact, exponents tells you how many times that particular factor is being used. Okay? And multiplicities have some relationship with x-intercepts. If r is a zero of even multiplicity like 2, 4, 6, 8, etc., the graph touches the x-axis and turns around at r. So a zero with an even multiplicity tells you that if you were to graph this, it's going to touch the x-axis at r and then make a turn. But if r is a zero of odd multiplicity like 1, 3, 5, 7, etc., the graph will be crossing the x-axis at that value of r. Okay. And I do have an example of just that. All right, let's look at this one. Let's say we want to find the zeros of this particular function. Here we got f of x is equal to negative 4 times x plus 1 half quantity squared times x minus 5, and that quantity is to the third power. And we're going to find the multiplicity of each zero, and then we're going to state whether the graph crosses the x-axis or touches the x-axis and turns around at each zero. Okay, so now in this case, that's the equation, and notice the equation is already factored out for you, so you don't have to worry about doing any factoring. Okay, like we did in the other two examples, because this equation is already factored out for you. Okay, so here, this is what we're going to do. We're going to take each binomial factor, like x plus 1 half, and set that equal to 0. And then the other binomial factor, x minus 5, that's going to be set equal to 0. And each one of these we're going to solve for x. So for x plus 1 half is equal to 0, you're going to have x is equal to negative 1 half. And then for x minus 5 is equal to 0, If you add 5, you get x is equal to 5. Okay, so the zeros of this function will be negative 1/2 and 5. Now we need to give the multiplicity for each of these zeros. For the x equal negative 1/2, that came from x plus 1/2 when I solved this equation. The exponent for x plus 1/2 is a 2. So that means x is equal to negative 1/2 will have a multiplicity of 2. And then for x equals 5, that came from x minus 5. The exponent for that is a 3. So that means that x equals 5 has a multiplicity of 3. Okay, so that's how we state the multiplicities. And then we state whether the graph crosses the x-axis or touches and turns around at each zero. Okay, for x equals negative 1/2, we have an even multiplicity of 2. So here we can say this. At the value of x is equal to negative 1/2, the graph of f of x, since it has even multiplicity, it touches the x-axis and turns around. Okay. That's at x equals negative 1/2 because it has even multiplicity. The graph is going to touch the x-axis and turn around at negative 1/2. Now for x is equal to 5, it has a multiplicity of 3, and it has an odd multiplicity. So we're going to say this: at x is equal to 5, the graph of f of x simply crosses the x-axis. Okay. And that's all there is to it, just stating whether the behavior of that particular graph at each zero. Okay, so that will conclude this particular section on polynomial functions and their graphs.